Alrighty, we are talking about IMF. What is IMF? Intermolecular forces. That is forces or attractions between two things, two objects. Could be two atoms, could be two molecules, could be two anything. Okay, how much force or attractive force is between those molecules? And we talked about a few kinds of interactions. Okay, can you name one of them? London dispersion is one of them. Another one is dipole to dipole, and another one is dipole to ion. Okay, all of them are van der Waals forces, and those are three of the ones under there. There was one more very special one. Hydrogen bond. Okay, so we have four intermolecular forces that are possible. Now, for any molecule, this is important, you may have more than one force working, but only one force will be the largest influencer or the biggest one. And so, every molecule has London dispersion force, where things get a little bit more unbalanced than normal. Even dipoles. Even dipoles are unbalanced all the time. London dispersion force lets them be even more unbalanced a little tiny part of the time. Now, a dipole interaction is much larger than a London dispersion force, but London dispersion force is there. In a non-polar molecule, or one molecule that is not a dipole, the only thing that you can have is London dispersion force. So that becomes the largest one. Okay. And so we looked at a couple of figures, and you guys picked this out last time, that in the case of these compounds, which had lots of carbons and hydrogens, okay, and then some elements that had electronegativity, there were some polarity differences. And we saw that by seeing an actual value called dipole moment. And as the larger the dipole moment, the larger the polarity, or the larger kind of dipole it has, the more attraction between two molecules are seen. And we can see that because of the boiling point. The amount of energy needed to pull them apart is greater the larger that difference in electronegativity. Okay. We also looked at these two graphs, and we found that in these there was no polarity, so they were all non-polar. And so the only thing that we could look at in this was the larger it became, then the more likely or the more imbalanced it can become instantaneously, and so more attraction can be seen. In this, we looked at the shape influences, especially London dispersion force, because if I can pack them closer together and have more surface area interacting between the two molecules, then there are more attractive forces that can be had between the two. And so the N-pentane was a little bit more attractive to each other than the neopentane. And we could see that again by the boiling point. All right. All is well and good in the world until you get to a real problem. All right. So here we go. This is the kind of problem that you have. Now, it's all abstract up to this point in time. Here we go. Which one of these has the largest London dispersion force? Okay. Talk with your neighbor. What do you think? Okay. All right. Anybody brave? Bromine. The reason why bromine of all of these has the largest is because of its molecular weight. It is the largest molecular weight, so it has the ability to become imbalanced more because there is more stuff to imbalance. Now, that doesn't mean that's the strongest intermolecular force of those molecules at the top. This I just referred to the London dispersion force because every one of them has London dispersion force. Okay? Which of these has the largest dipole attractive force? Discuss. We leave nothing behind. We leave nothing behind. Okay? So what's the principle that we look at? What is the inherent property of the atoms that we have to look at to determine if we have polarity? Electronegativity. So we have to know the trend for electronegativity. And so, can this one be polar? No. Can this be polar? It doesn't even have a bond, so no, it can't be polar. Can this one be polar? Yes, it can. So we got one candidate. Can this be polar? The next one. Yes. Can this be polar? No. So we have two candidates. All right. Now, when I'm comparing this, one side of the bond is hydrogen for each of them, and then there's something different on the other side. So, in this case, I have to look at the difference between chloride and bromide. Which one is more electronegative? Chlorine. Okay? And so, in terms of partial, this side is a delta negative, this side is a delta positive, or I could also say that one side is positive, one side is negative by writing it this particular direction. The bond is polar. Is this molecule polar? Yes, it has to be because there's nothing pulling on the other side that is of equal value, and so it is polar. This is the largest dipole attractive force. Is there any other force that I can have? Can I have ion dipole interactions in that grouping? No, why? You have no what? You don't have any ions. Okay. Can I have a hydrogen bond? No. I have hydrogens, but what else do you need? N, O, or F to have a hydrogen bond. I don't have any of those atoms. Okay. All right. Listed in decreasing order, ion dipole has the most energy, stabilization, hydrogen bond following, dipole following, and London dispersion force. And the last three are dependent upon if it is polar, a dipole moment, its molecular weight, and its shape to fully flesh out exactly how much attraction that you're going to have between. Now, you're never going to be able to tell me a value of attraction. Okay? There's no math in this one, but you can do comparisons between things. Or you can identify what forces are available. Now, the book has a table, a figure that you can go through this. What you really have to do is look at what the molecules are that are interacting. Then you have to decide what kind of thing it is. Now, are there polar molecules involved? How in the world do you know if it's polar? Okay, ions would actually have some polarity in it, yes. And that's a special case because I've got negatives and positives. But how do you tell if a molecule is absolutely polar?
You look at the electronegativity.
You have to look at the electronegativity of the bonds, but that's not all. You have to look at the Lewis structure. You have to look at all the bonds, and you have to know that, there are bonds that are polar, but you have to make sure and exclude any one that is balanced and becomes nonpolar. Okay? So that whole problem that we had before was just tell me if it's polar. Now I want you to tell me if it's polar, and then how does it behave in real life? Wow. Okay. And so this will build. So if there are ions involved, I have two possibilities. I can have an ion and a dipole interacting. That is an intermolecular force. Or I can have two ions coming together, a positive, negative, that classifies it as a bond, an ionic bond. Okay? If by chance I have polar molecules, then do you have the possibility of having NOF? Then there's a possibility of having a hydrogen bond, so you have to eliminate this, or it's a hydrogen bond. If it is not a hydrogen bond, then it is a dipole-dipole force. If it is not polar, the only thing that you can have, and the largest one that you can have, is London dispersion force. But in all of these cases, London dispersion forces are a small fraction of the energy. What we usually, though, is identify most often which one is the most influential, but there may be a question that asks you, what are all of the possibilities? Oh, okay, here. Identify the intermolecular force present in the following substances. Okay, CH3, which is correspondingly that one. CH3OH was correspondingly this. And C3H2OH here. This is called ethylene. Here, this is called methanol, and this is called ethanol. All right. What kind of intermolecular forces can you have with this one, and then with this one, and then with that one? Talk. Hmm? Ah, okay, very good. The Lewis structures are not complete here. I will complete your Lewis structures. There you go. There is complete Lewis structures. Do you feel comfortable with this? Do you feel uncomfortable with this? Okay, biggest piece of the puzzle. When I ask this question and you look at this one right here, you're saying if two of these interact between themselves, okay, what kind of things can it have? Does it have an ion? Is that an ion? No. Then ion dipole is out completely. I'm left with three more. Does this have nitrogen, oxygen, or fluorine? No. Then I get rid of what completely? Hydrogen bond. I'm down to two. Is it a dipole or not? Okay. Here is the answer to that question. When you look at bonds, they're nonpolar if they're bounded to themselves, just like this one. That's nonpolar. And by definition, any carbon to hydrogen is nonpolar. If every bond is nonpolar, then the molecule is nonpolar. If it is nonpolar, it is not a dipole. So what have I eliminated? Dipole. And so what is the only thing I can have? London dispersion force. Okay. Second one. Is there an ion? Nope, no ion dipole. Is there NOF? Yes. There's NOF there. Okay. Now, you have to have between the two a hydrogen bound to an oxygen. Do we have that? And we have on the other one, we have to have an oxygen, nitrogen, or fluorine that has a lone pair. Would the other one have that? So what kind of force do we have? hydrogen bond. Okay? Then hydrogen bond is a specialized dipole-dipole. So we're not going to say dipole-dipole. What else does it have? It does have London dispersion force. Now, not S, force. Now, hydrogen bond is so much larger than London dispersion force, we don't really care, but it just said, this question said, what are all of them? That's why we place it. All right? So what do you think about ethanol, this next one? What do you think about its ability? What does it have?
It's a
Hydrogen
hydrogen bond.
bond and London dispersion force. Okay, great. All right, B. Which one has the highest boiling point? That is saying, another way of saying which one attracts to each other stronger. Okay. Which is the weakest? The first one, right? London dispersion force. So that one's totally off the board. But I have two that have hydrogen bonds and London dispersion force. So how would I compare that? It would be the last one. It is because of more molecular weight. There is one hydrogen bond that is exactly the same with both, so the hydrogen bonds will kind of negate one of them, each other, because they're the same strength. But then when you learn to move to London dispersion force, the larger one would win out. And so it has a larger London dispersion force, the same hydrogen bond, so the last one would have the highest boiling point. Okay? That's a whole lot different than PV equals nRT, right? These kind of questions. And so it's a thinking process that you cannot check with your calculator. All right. What in the world are these London dispersion forces doing? They're going to affect physical properties. Okay? And so there are a couple of physical properties that we're going to identify that control things like boiling point, melting point, vapor pressures, viscosities. When we talk about surface tension, how these molecules will attract together will give different properties to solutions and or solids. Here's the deal. The larger the attraction, the more energy it takes to overcome things, okay, or to pull them apart. We have been using boiling point at this moment in time because it's the most or the largest amount of energy to that's associated with a physical property. The first, viscosity. Viscosity is how well a fluid flows. So something that is not very viscous is water. It flows very readily. Okay? Something that is very viscous is honey. Okay? And so if you take a bottle of honey and you turn it over, is it all just going to flop out? No, it takes a long time sometimes for the honey, and I get frustrated, and so I squeeze the bottle. And that's not flowing anymore. I'm putting force in it to get it out. Okay? And so it is a property that is the resistance of the liquid to flow, and viscosities will increase with larger intermolecular forces. And so there is a viscosity value for things. And in the case that we see with the formulas, all of the bonds are carbons and hydrogens, so these are all nonpolar. But as you can see, the larger they get, the larger the value of viscosity, because London dispersion forces increase as you get larger. All right? Now, viscosities will, if you give it enough temperature though, it will change. And so if I heat up a molecule, then they have more kinetic energy, they overcome the attractive forces, they can flow better, they can flow faster. Now, if I take a look at these examples, methyl glycol, ethylene glycol, and glycerin, okay, I can even arrange them in what I would predict to be increasing viscosities. And so which one would be the most viscous of these three? Methyl glycol, ethylene glycol, or glycerin? Let me complete the drawings. Assuming the book gets these right, sometimes they don't use lone pairs. You have to fill in the lone pairs yourself to make octet. Most books are right, not always, but most books are right. We're looking at the ability to hydrogen bond. Okay, so the most viscous would be which one?
Glycerin.
This one, the one that has 3 glycerol, 3 hydroxides. That means for every one of those molecules, they could make potentially 3 hydrogen bonds. They get stuck together. Glycol is very, very thick. Ethylene glycol and methyl glycol both have 2. They can make 2 hydrogen bonds. Which one would be a little bit more viscous? Not the methyl. The ethyl, because it has a little bit more London dispersion force. Okay? And so we can talk about properties. We can talk about boiling point. We can talk about viscosity. Surface tension is a pretty interesting thing. Surface tension is the net inward force experienced by the molecule on the surface of a liquid. The one liquid that we see that has a lot of surface tension, because water molecules are very, very polar, is water. And you can see the bug is actually standing on the water. Okay? It actually exerts a pressure pushing down on the water, but the water is attracting to itself so much that there is a level of ability that it can carry a little bit of weight before it breaks, and so water bugs can be on the top. And do you see the water bubble on top of the penny? It doesn't flow. If you are very careful, you can make that happen, but you can also overcome surface tension and then it'll flow. But surface tension is an important aspect, especially seen in things that are polar. If you have non-polar molecules, very little surface tension is associated with them. Solubility. Okay. Ooh, remember those rules? Okay, you should remember those rules. You probably should go back and take that TRQ again, because those rules are going to come back up. Solubility, as we said, if it's aqueous. Well, here's really what happens. The water molecule, which is polar, likes to attract the positive, negative polar ions, and so like things will dissolve like things. Polar dissolves polar, non-polar will dissolve non-polar. And so the IMF forces, the intermolecular forces of non-polar substances, cannot overcome the polar molecules like a salt, because the non-polar just doesn't have enough energy to make a strong interaction. It would rather be placed together with positive charges. All right, next concept are solids. Okay, something is solid because why? Say that again? Yes, they are. Molecules are so tight together that they are moving but vibrating, but not moving past each other. I know it's a solid because it takes up a definite volume and it has a definite shape. It keeps its own shape. So there's enough attraction between the molecules that they don't fall apart, and there's not enough energy for them to slide past each other. There are 2 kinds of solids. One that I would define, it's like my wife and me, okay? One is very ordered and meticulous, okay? And the other is all over the place, okay? And so we describe this as, and they're just 2 different ways of doing things, right?
Which one are you? The meticulous.
Yeah. Yeah. Little meticulous. Okay. Things should have a place, and things should go into that place. You know, that's how I feel. But then there's the pile method. It's in one pile. I can find it. Okay. And when I change her system by organizing it, it's really bad. And she doesn't let me in the kitchen too often because I won't. She can't find anything. Although I put all of these. Not okay. Neither here nor there. All right. Ordered structures are crystalline. Okay. There's a repeating pattern. Okay. They self-pack. They tend to be more dense because I get more stuff in a smaller volume. And so there's an ordered arrangement. Amorphous solids are there. Just kind of thrown in there. Yeah, it's like amorphous and crystalline is like whether I pack the trunk in the car to go somewhere or my wife packs the trunk. If it all gets in there and shuts, it's okay for my wife. Got to lighten up. Yeah, makes me feel uncomfortable. Don't do that. Okay, and so those are the two ways about it. Okay, and so amorphous and crystalline solids are the two types of solids. Thank you, guys.